Greetings, ladies and gentlemen. I welcome you all to our today's lecture. In our today's lecture, we shall talk about dimension of a vector space. However, before we talk about a dimension of a vector space, let us recall some few concepts that we studied in our previous lecture. So in our previous lecture, we talked about a basis of a vector space. And basically we said that for a non-empty set S of a vector space V will be called the basis of V if it satisfies two conditions. That is, S is a linearly independent set, and two, every vector in V can be uniquely expressed as a linear combination of the elements of S. If the two conditions are satisfied, then we shall call that given set a basis of that same set. That is a basis of the vector space V. Now, I gave you some of the trial questions, and I hope you were able to show that the given sets were either a basis of the vector space or not, depending on what you got as your answers, whether the two conditions were satisfied or not. Now, let us talk about dimension of a vector space. We shall be defining the dimension of a vector space basically by looking at the number of elements in the basis of a vector space. Now, we shall say that the number of elements in the finite basis of a vector space V over a given field F is called the dimension of the vector space. So if we want to know the dimension of a vector space, we look at how many elements are within the basis of a vector space. Meaning, to define a dimension of a vector space, you must first of all look at the basis. And I hope you know how to get the basis, or to show that a given set is a basis of a vector space. So when you look at the number of elements in that basis, then that number will give you what we call the dimension of that given vector space. For example, let us refer to some of these. Let us refer to some of these questions here. For example, when you look at this number 5, we are saying show that the vectors S are the vectors in S, which S is given by this, form a basis for R3. So if we want to know the dimension of R3, basing on this basis here, we look at, first of all, you must first of all confirm whether this set here is actually forming a basis. If it forms a basis, then we shall count the number of elements in this basis. So let us suppose that this S here is a basis of R3, meaning it satisfies the two conditions. Now, having confirmed that this S here is a basis, we now look at the dimension for the vector space. What is the dimension? The dimension will be basically the number of elements in this vector, in this basis here. So the number of elements, we have 1, 2, 3. So we shall be saying that the dimension of this vector space R3 will be 3, because there are 3 elements in the basis of what? In the basis for this vector space. So the number of elements, 1, 2, 3, will give us the dimension of the vector space. The same applies to this. If you have shown that these elements here form what we call a basis for R3. So if we are interested in the dimension for R3, then we look at the number of elements in this basis. And how many elements are they? 1, 2, and 3. So there are 3 elements. The same applies to this question number 3. If you have shown that 1x, x squared up to xn forms a basis of Pn of R, that is a set of polynomials over R, then we shall say that how many elements, if there are any of them, if there are any elements of them, 1, 2, 3, up to x to the power n, then it means the dimension of this vector space P of n will actually be n. So that is how we determine the dimension. But let us now look at what we call the finite dimensional vector space. So before we come to the finite dimensional vector space, let us look at the abbreviation. We shall sometimes be using dim_v to represent the dimension of the vector space V. So when you say the dimension of V is equal to n, then it means that this is an n-dimensional vector space. And in other words, in the basis for this V, there will be n elements. When we talk about a finite dimensional vector space, a vector space over a given field F will be said to be finite dimensional if it has a finite basis, meaning that the elements in the basis are countable. So for that case, we shall say that the vector space is finite dimensional. However, we shall say the vector space is infinite dimensional if it has got an infinite basis, meaning that the elements within the basis set and elements within the basis set cannot be counted. So we shall say that that given vector space, or the vector space whose basis has got an infinite number of elements, we shall call it an infinite dimensional vector space. So these are the two different types of dimensional vector spaces: finite and infinite. And the dimension, as we have said, depends on the number of elements within a vector space. We shall look at some few examples of what we call dimensions for different vector spaces. For example, when we talk about dimension of R to the power 2, the dimension of R to the power 2 over R, that is over the field R, is 2. Because within the basis, we shall always be having two elements, 1, 0, 0, 1. When you look at these two elements here from R2, because we can see 1, 0 is an element from R2. Then 0, 1 is an element from R2. But when you look at these two elements here, when you test whether they form a basis of R2, they will surely satisfy. So you have to test whether they are linearly independent and whether this basis B spans R2. They will surely satisfy the two conditions. So the dimension of R2 is 2. The dimension of R2 is 2. And for that case, the basis, this is what we call the basis of R2 over R. So it contains elements 1, 0 and 0, 1. They will always satisfy the conditions for the basis. Then when we talk about dimension of R to the power n, dimension of R to the power n is actually n. So the dimension of R to the power n is n, and its standard basis, the standard basis, contains elements of this nature. That is, you can have the basis having 1, 0, 0, n terms. Then the next one will be 0, 1, 0, 0, up to 0 again. So the trend continues up to the last term, that is 0, 0, 0, up to the last value, which is a 1. So when you look at these elements here, they will surely satisfy the conditions for the basis. And for that case, if we want to know the dimension now of the dimension of R to the power n, then we shall simply count how many are they how many elements are in this basis. So the standard elements are this one, and the trend continues up to the last value. So we can count them 1, 2, 3 up to the nth element. So there are n elements in the basis for R to power n. So these are the standard elements within this given set. Meaning that if they change a bit, then it means we also need to change the condition on R to power n. But for the standard basis, this is the standard basis. They also, when, for example, you talk about R3, then the standard basis for R3 becomes 1, 0, 0. This is 1, 0, 0. Then you have another element. This is one element. Another element is 0, 1, 0. Another one is a 0, 0, 1. So this becomes the standard basis of R3. So the standard basis of R3 contains 3 elements. This is the standard basis for R3. The same applies for R4. It means the standard basis for R4 will contain 4 elements, and they should be of this nature: 1, 0, 0, 0, like that, 0, 1, 0, 0. They will always satisfy the conditions for the basis. So that is R to power 4. So meaning that when we are talking about dimension of R to power 5, if you want over R, the dimension of R to power 5 over R will surely be 5. Dimension of R2 over R will be 2. And these are the standard elements within the basis. Remember, to determine the dimension, we must first of all know how many elements are in the basis set. So that is for the case of dimension of R to power n. Then when we talk about dimension of A, which is that is the vector space, matrix vector space of this is Mn. So when we are talking about Mn over R is M times n, meaning that when you are talking about dimension for which you are considering a vector space of all maybe 3 by 3 matrices, this is the dimension of the vector space of 3 by 3 matrices. So the dimension of this one will simply be 3 times 3, and the dimension will be 9. So we have taken an example here, dimension of M3, that is the dimension of all the vector space consisting of 3 by 2 matrices. So the dimension of a vector space consisting of 3 by 2 matrices is simply obtained by multiplying this. So if we are considering 3 by 2 matrices, so the vector space, if we want to know the dimension, then we simply get 3 times 2, then which will give us a 6. So that is for matrix space. Okay, so then we talk about the dimension of R over R. The dimension of R over R is 1, and its basis is 1. That is R, real number over R. That will always be 1. Even if it becomes the dimension of C, if you are talking about the dimension, for example, of C over C, so dimension of a vector space over the same, the field which is the same now, then it will always be giving you 1. So when you are to look at the dimension, maybe they tell you K is a vector space. There's a vector space of some elements. Then they tell you what is the dimension of K, which is a vector space K over the field K. Then it will always be 1. Dimension of the complex space over the same, that is complex space, it will always be 1. The dimension of F over F, again over F, it will always be 1. So the dimension of vector space over the field which is similar to that space you are considering will always be 1, and its basis will be containing 1. Then other than that, we can also talk about, for example, the dimension of the complex space. If you consider the dimension of the complex space, that is the dimension of C over R, when you are considering dimension of C over R is 2. And what will be the basis? The basis will contain 2 elements, that is 1 and I. So that will be the basis of C over R. But as we said, if it is C over C, then it will be 1. F over F, it will be 1. So that will be the basis for C, because we know complex numbers can be represented by the real part and imaginary part. So the real part, when you consider 1 and I, this one will always satisfy the conditions for the basis. So these are the standard elements within the standard basis for C over R. Let us now look at some examples. For example, this one says find the basis and dimension of the solution space in a system. So we are given a homogeneous system and we need to find the basis and dimension of the solution space. So let us first of all get the solution space and see how best we can find the basis and the dimension. So we are given x1, we are given x1 plus x3 plus x5 equaling to 0. We are given x2 plus x4 plus x5 equaling to 0. We are given x1 plus x2 plus x3 plus x4 equaling to 0. We are also given x3 plus x4 equaling to 0. So we shall find the solution space by first of all solving this using elementary operations. So let us first get the augmented matrix. So the augmented matrix will be, we shall be having, this is 1 0 1 0 1. Here we are having 0. This is 0. X2, this is 1. X3 0. X4 is 1. X5 is 1. Then next we shall have 1. X2 is 1. X3 is also 1. X4 is 1, meaning X5 is 0. Next we shall have X1 0, X2 is 0, X3 is 1, X4 is also 1, this is 0. So we shall have 0 0 0. Let us use row operations to form, we shall need to form echelon matrix. So to form the echelon matrix, let us look at how best we can eliminate this first. So it means we shall use the operation negative row 1 plus this is row 3 to give us row 3. So when we do that, we shall be able to maintain all others constant, 1 0 1 0 1. We shall be able to maintain 0 1 0 1 1. We shall be able to maintain the last one. So let us first compute this. When we put this operation here, we shall be able to get, this will give us a negative 1 plus 1, this will be 0. This is 0 plus 1, which will be 1. This will be negative 1 plus 1, that will give us a 0. This will be 0 plus 1, which will give us 1. This will be negative 1 plus 0, which will also give us negative 1. This is negative 1. So we shall be able to get here negative 1. We are getting negative of this plus this. This is negative 1. So we shall have 0, 0, 0 here. So the last one is 0. The last one is 0, 0, 1, 1, 0, again 0. So we shall have that. Next, we can now eliminate this because we want the reading value to be 1. So let us also eliminate 1 here. We shall use row 2. So that is negative row 2 plus row 1 to give, this is row 3 plus row 3 to give us row 3. When we do that, we shall also have 1, 0, 1, 0, 1. This is 0. We shall still have 0. This is 1, 0, 1, 1. This is still 0. When we apply the operation, it will be 0. This is negative 1 plus 1, 0. This is 0. This will give us 0. So this is negative 1 plus 1. It will still be 0. Next, we shall have negative 1 plus negative 1. It will be negative 2. And this one here will still be 0. So next, we shall have this as 0, 0, 1. This will also be 1. This will be 0. And this will be 0. So that is what we shall have. Next, we can make some, because we are having 0, 0, 0, 0 here. So let us try to interchange row 3 and row 4. Row 3 to be row 4 and row 4, such that this one comes in the last row. So row 3 to become row 4 and row 4 to become row 3. So that one will give us. So when we do interchange row 3 to become row 4 and row 4 to become row 3, we shall be able to bring this one here and this one will go there. So we shall now obtain this matrix. So from there, we can also eliminate this negative by placing negative a half, row 4 to give us row 4. So when we do that, we shall be able to obtain 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, then 0, 0, 0, 0, 1, and here we are still having 0, 0, 0, 0. So this is what so far we have. Now from here we can see that we have expressed this in echelon form, so we can get our system back. So when we get our system back, we shall say the corresponding system. So the corresponding linear system will become x1. Remember, this represents, we have x1, x2, x3, x4, and x5 as our variables. So that is x1, x2, x1 plus 0, x2 plus x3 up to x5 is equal to 0. Then x2, then plus x4 plus x5 equaling to 0. Then x3 plus x4 equaling to 0. Then x5, this is 1, x5 is equal to 0. So from here, we already have x5 as 0. So from here, we can obtain x3 as negative x4. Clearly, we can see that the free variable now will be x4. The free variable will be x4. So what we can do is to let us let x4 to be like t. If we let x4 to be like t, it means x3 will be negative t. When we come to this, x2 plus x4 is t, so this is t, plus x5 is 0, will be equal to 0, meaning x2 is equal to negative t as well. Then when we look at this, x1 plus x3, we have seen x3 is this, negative t, plus x5 is 0, it will be equal to 0, meaning that x1 is actually equal at positive t. So we have x1, x2, x3, x4 is t, and the x5 is 0. So this one here, t is any parameter. T is any parameter from a set of real numbers. So if that is the case, so we can now rearrange to have x1, x2, x3, and x4, x5. x1 is t from what we have obtained. x1 is t, x2 negative t, x3 negative t, x4 is t, then x5 is 0. So from there, that's why we are having t, negative t, negative t. So when we pull out the t, we shall be able to remain with 1, negative 1, negative 1, 1, and 0 into t. So if we need the basis, if we need to obtain the basis, so we shall say for the basis, because this is our solution space. This is our solution space. So to obtain the basis, we shall set t to be like 1. If you set your t to be like 1, we shall be able to obtain, so we are getting our basis. So we are setting t to be like 1. When you set t to be like 1, then we shall be able to obtain x1, x2, x3, x4, and x5. This one here will be 1, negative 1, negative 1, 1, and 0. So when you obtain this, this will be your basis. So the basis set is containing 1, negative 1, negative 1, 1, and 0. So this is your basis set. So having obtained this as your basis set, what is the dimension? So the dimension, so this is the base set. Of course, we can easily see that it is containing 1, 2, 3, 4, 5 elements. So it is a base set from R5. This is a base set from R5. So what will be the dimension? The dimension of the solution set. So the dimension will now be 1. The dimension is 1 because it is only one element in the basis set. It is only one element in the basis set. So that is how we obtain the dimension and the basis for the given solution space. So to obtain the basis and dimension for a homogeneous system, first solve the system normally and make sure that you express it in echelon form. Then having expressed it in echelon form, then get the solution. So the solution, the number of free variables that you will have in your solution set will determine the dimension and the basis for the given solution space. So that is how basically we obtain the basis and dimension. Let us look at example number 2. We need to determine the basis and dimension of the solution space for the homogeneous system. So we have two numbers. You try out part A and let us try together part B. So part B, we need first of all get the solution space, then after we can get the basis and dimension. So from part B, we can write, so from the augmented matrix, this is our augmented matrix, we shall have, this is our augmented matrix. So we shall now apply row operations. So we shall place operation which is -3, -3 in row 1 plus 2 in row 2 to give us row 2. We shall apply -5 in row 1 plus 2 in row 3 to give us row 3. So -3 times 2 plus 2 times 3, we shall be able to get -6 plus 6, which is 0. This is -12 plus 2 times 6, which is -12 plus 12, that will also give us 0. Then the next one, this is -5 times -3, which is 15, plus -14, this will give us +1. Then next we shall have, this will be -9, this is -9, plus this will be 8, and this will give us -1, and this will remain 0. Then pressing this operation, this is -10 plus 10, which will also give us 0. This is a -20 plus 2 times 10, that is +20, so -20 plus 20 minus 20 plus 20 will give us 0. Also, when we apply -5 times -5, that is +25, then plus -22. So that will give us 3. Then next we shall apply -5 times 3, that is -15, plus 12, -15 plus 12 will give us -3, and this will remain 0. So next operation, we can apply -3 in row 2 plus row 3 to give us row 3. We shall also apply a half in row 1 to give us row 1 to make this one 1. So for that case, we shall have 1, 2, -5 by 2, this is 3 by 2, and this will be 0. Then this will remain the same, 0, 0, 1, -1, this will remain 0. Then we shall have 0 here. Then applying this operation, this is 0, this is 0 still. -3 times 1 plus 3, this will give us 0. -3 times -1 will be +3, plus -3 will give us 0. So this will also be 0. So for that case, we shall have our echelon form. So our echelon form will now be this one here. So we need now to have the linear system. So the corresponding linear system is, so we shall have x plus 2y minus 5 by 2z plus 3 by 2 t, which is equal to 0. We shall have z minus t, which is equal to 0. So from there, we shall try now to rearrange. When we make, for example, x the subject, if we make x the subject, so we can take this one this side, or we can first of all look at our free parameters. meaning we can express z in terms of t. But when you look at this, it means we shall have z in terms of t. So we can relate t, then but also y. So we shall relate our free variables. So we can see we have two free variables, y and t. So let us let t to be like p and y to be like q. So that is what we have. So from this we shall have z equaling to p. Then next we can also have, so we can also have x here. So this will mean also that x plus y is 2, so 2q, then minus 5 by 2 of z is p, plus 3 by 2 t is p, so this will be p, this will be equal to 0. So clearly we can try to simplify this. We have negative 5 over 2p plus 3 over 2 also p. So in other words, negative 5 LCM is the same. Negative 5 plus 3 is negative 2 divided by 2, it will be a negative 1. So we shall remain with x plus 2q minus p equaling to 0. So for that case, x plus 2q minus p will be equal to 0, which means x is same as negative 2q plus p. So what do we have? We have x, we have y, z, and t. So let us try to have our solution. So this is our solution now. So this solution will be, what is x is negative 2q plus p. What is y? We need y here. Y is q. Y is q. Then we need z. Z is p. We need t. T we had let it to be p as well. So y is q. Y is q. Then z is p and t is p. So that is what we are having. So this is what we have, but we can rearrange this. This is negative 2q. Then this one here is q. This is p, so that is 0, 0. Plus we can have this one here is p. This is q. It means here we have 0p. This is p, and this is p. So for that case, we can have this as negative 2, 1, 0, 0. This is into q, plus we can have this as 1, 0, 1, 1 into p. So this is our x, y, z, and t. Now we need to obtain the basis. We need to obtain the basis and the dimension. But remember, p and q are elements from R. So these are parameters, where p and q are parameters, but taken from the set of real numbers. So from here, what will be the basis? To obtain the basis, let us write it here. To obtain the basis set. So the basis 1, we can set q to 1. We shall set q to 1 and p to 0. So set one of them to 1 and another one to 0 to get to 1. So it means one of the basis vectors or the elements in the basis, we shall have, when we set q to 1 and p to 0, we shall remain with negative 2, 1, 0, 0. Then again set Q to 0 and P to 1. Set one of them to 1 and another one to 0 to obtain the basis vectors. So when you set Q to 0, it means this will go to 0. P to 1, you will remain with this. So you remain with 1, 0, 1, 1. So these are the elements in the basis vectors. If it is only one like this, so set Q to 1. But if there are two, set one to 1 of the parameters to 0 and another one to 1. If there are three, it means you will set one to be like 1, and others to be zeros, another one to be 1, others to be zeros, another one to be 1. So you set parameters 1 or 0, depending on how many they are. If they are 2, set, for example, here we are setting Q to 0, maintain P, so set P to 1. Set Q to 0 or to 1, then maintain this one to 0. So that is what we shall have. So the basis set will be containing -2, 1, 0, 0, then 1, 0, 1, 1. So this will be the basis. So having got the basis, we can now obtain the dimension by simply looking at the number of elements in the basis. So this is our basis element, this is our basis element. But clearly we can see that these are elements of r to power 4 because we have 1, 2, 3, 4. So that is obtained from r to power 4. So clearly we can now obtain the dimension of the solution set, and the dimension will basically be 2 because we have only 2 elements from our basis set. So the base set we have obtained is this. So look at the number of elements in the base set, and that will be the dimension. So the dimension is 2, and these are the basis elements, or the elements within what we call the basis set. Let us talk about the dimension and the subspace. When you have a vector space V, and a subspace, so this is our vector space, then the subspace, and we have the subspace W. Then if the dimension of the vector space is n, then we shall always be saying that the dimension of the subspace will always be less or equal to the dimension of the vector space. So that's why we say dimension of W, which is the subspace, is less or equal to n, which n is the dimension of the vector space. And in case the dimension of W is also n, then it means the subspace is actually equal to the vector space. So that is when the dimension of the subspace is equal to the dimension of the vector space. So if the two have the same dimensions, then it means the two are also equal. That is the subspace and the vector space. So we can easily prove that. Because we understand that when we understand that if V is the dimension, if n is the dimension of V, then it means the basis of V contains n linearly independent vectors. Because you understand that for a basis to be formed, then we must satisfy the two conditions. That is, the set of B must be spanning the vector space, and at the same time, the elements or the vectors within this basis must be linearly independent. So, and as we said, to determine the dimension of the vector space, you must look at the number of elements within the basis. So that's why we are saying, since V is of dimension n, it means the moment you have more than n vectors within the basis, then it means they will be linearly dependent. We looked at that case in our previous lecture. If you are talking about r to the power n, it means if this is our vector space r to the power n, it means it is n dimensional vector space. Then the moment you exceed the elements within n, then they will no longer be linearly independent. So, but n plus 1 or more vectors in r to the power n, it means they will be linearly dependent, and that set will no longer be satisfying the conditions for the basis. So we are saying that if V is of dimension n, then any n plus 1 or more vectors are linearly dependent. That one we also looked at the theorem and the proof for that. Then, furthermore, we understand that since a basis of W consists of linearly independent vectors, then obviously it cannot contain more than n elements. It means the maximum must be n. The maximum must be n. The moment it exceeds, you have more than n vectors in the basis, it means they will be linearly dependent. And that one will no longer be a basis. And it means if it does not satisfy the conditions for the basis, then it means it will no longer give us the dimension of that given vector space, because the dimension of the vector space is determined by the basis, and the basis is determined by the linearly independent vectors. So if the dimension of V is n, then it means the basis or the elements in the basis cannot exceed n, because it is only n linearly independent vectors that will be in W. It can be n or less, but it cannot be greater than n. So we are saying it cannot contain more than n elements, and accordingly, that's why we can say dimension of W is less or equal to n. And in particular, if you find that within W, the elements that are in W are, for example, W1, W2 up to Wn, it means this basis, the basis of our basis, the elements in our basis are actually n in number. So it means, in particular, if we have this set consisting of W1 up to Wn, it means the elements within this basis will be actually n. And if they are n, then it means they will be the n linearly independent vectors. And for that case, it means this will actually be the same as the basis of V. Remember, the basis of V is also containing n elements. And also, we can see that this basis of the subspace is also consisting n elements. So in that case, we shall actually say that the subspace and the vector space are actually the same when the dimension of the subspace is actually equal to n. So this will be a simple proof to show that the dimension, if the dimension of vector space is n, then the dimension of the subspace will always be less or equal to n. Because the moment they exceed n, they will no longer be linearly independent. They will actually become linearly dependent, and of course they will not satisfy the condition for the basis. And if you don't have a basis, you cannot determine the dimension, because the dimension is obtained from the basis. You look at the number of elements in the basis. So we shall talk about this question here. It says, let W be a subspace of a real space R3. So we want to give the geometrical description of W in terms of its dimension. And we are saying that since we are talking about the vector space which is R3, it means the dimension of our vector space for our case now is actually 3. So if the dimension is 3, then the dimension, as we said, that the dimension of the subspace will always be less or equal to the dimension of the vector space. So it means the dimension of W can be less or equal to what? To 3, because the dimension of R3 over R is 3. The dimension of R3 is 3. So which means if this is our vector space and W is a subspace, then the dimension of W will always be less or equal to what? To 3, but cannot go beyond 3. So which means the dimension can actually be, the dimension of W can actually be 0, 1, 2, or 3. It can be 0, can be 1, can be 2, can be 3, but it cannot go beyond 3, which is the dimension of the vector space. So if the dimension of W is 0, then we shall have W which is containing a 0 vector, and for that case we shall call that one there a point. That will be a point. And if the dimension of W is 1, then it will be called a line through the origin. If the dimension is 2, then we shall be having that one there, as we call it the dimension, or we call it a plane through the origin. If it is a dimension is 0, then that is a point. If the dimension is 1, we call that one a line, and if the dimension is 2, we call that one a plane through the origin. But in case dimension is 3, then it means the dimension now of the subspace will be equal to the dimension of the vector space, and that's why we call it the entire space. So it means if the dimension is 3, then you are considering W as the entire space of R3. We shall now look at some examples regarding the basis and dimension of the subspace of a given vector space. So we shall look at example number 1 here. It says find the basis and dimension. Find the basis and dimension of the subspace W of R power 4, which is spanned by these vectors here. So the subspace W of R4 is spanned by these vectors. So what we shall do, we shall have our augmented matrix as 1, -4, -2, and 1. So this is 1, so make sure you arrange them in a row form. So we shall also have 1, -3, -1 and 2, then 3, -8, -2 and 7. So what we shall do is we shall row reduce this one here to echelon form. So when you place it in echelon form, then the non-zero rows will become what we call the basis. So simply row reduce this by using operations. You can apply your operations, then row reduce until you are able to get this matrix here. So after getting this matrix, then the non-zero rows, this one, 1, -4, -2 and 1, 0, 1, 1, 1 will become the basis elements. So this one, this row here, and this one here will form what we call the basis. So this will be the basis elements. In other words, our basis will be containing 1, -4, -2, and 1. And then 0, 1, 1, 1. So make sure you row reduce up to when you are able to obtain the echelon form. So when you row reduce, you should be able to reach at this given matrix, and the non-zero rows will become your basis elements. So looking at this, we can easily determine the dimension. We can easily determine the dimension of this subspace. This is the basis of W, is the basis of W. So the dimension of the basis of W is actually 2. So the dimension will be 2, and the basis will be these non-zero rows. Yeah.